Okay, intermolecular forces are specially dedicated to discrete molecules. So we are going to talk about intermolecular forces only when we have molecules. Why we talk about intermolecular forces? Because the intermolecular forces are going to allow us to explain why, for example, water is a liquid at room temperature and ammonia is not. Why hydrogen chloride has a very low melting and boiling point comparing with hydrogen fluoride that is very high. Okay, that is in molecules. And what about ionic compounds or covalent compounds? When we need or giant covalent compounds, when we need to separate the ions from a lattice, a metallic lattice, let's say that I have a metal here, okay, and the electrons around. For the metallic bonding, if I need to melt this, I need to overcome the forces that attract these particular ions from the rest. Okay, so I'm going to have this thing to be out. Yes? Why? Because I want to take them out from the lattice, which is solid, and put it as a liquid. And even worse, if I want that to be a gas, after I melt this, the ions are going to be all packed together in random directions moving, but they are going to still be some attraction between one and another atom. We need to take them out from the liquid. Okay? Now, in the case of the metals, we are not going to talk about intermolecular forces because intermolecular means molecules only. Yes? So we are going to see how the intermolecular forces varies with the different kind of molecules. And we already saw the shape of the molecules, and we already saw which molecules are polar and non-polar. So we are going to talk about the different molecules right now. The first thing that we are going to see is what happens when a molecule is polar. Let's say that I have hydrogen chloride. Yes? The molecule of hydrogen chloride is not symmetric. Why is not symmetric? Because the chlorine is more electronegative than the hydrogen. So I'm going to have a kind of density negative here and a density positive here. That makes this one to act as a dipole. Dipole means that it has two poles, a positive and a negative. It's not a charge. Yes? It's not an ionic bonding. It's a covalent bonding. We have a bond here, a covalent bonding. But we are going to have the electrons spending more time around the chlorine because it's more electronegative. Is that clear? Good. Now, what happens if I have another molecule of hydrogen chloride here? I have the hydrogen and the chlorine again. So I'm going to have an interaction in between these two molecules. And that interaction is going to be what we call intermolecular forces, that instead of only one dash for a pair of electrons, we put it as a dash line. That means intermolecular force. It's not a covalent bond, it's then an intermolecular force bond. Yes? So far so good? So, what happens here? This intermolecular force has to be overcome when we need to boil this. Okay? So the hydrogen chloride is a gas. But if we cool down the gas at lower temperatures than the boiling point, it's going to become a liquid. That means that these intermolecular forces are going to be present. What we need to do is to break them up to these molecules to be separated. So these intermolecular forces doesn't exist anymore. Yes? And that is going to be becoming a gas. Depending on how strong the intermolecular forces are, we are going to have molecules that are polar or non-polar, but they are in the molecular form. They are covalent compounds, but they boil at different melting and boiling points, or they boil at different temperatures. Yes? So in this case, we are going to have the dipole, the section dipole, dipole. Why dipole, dipole? Because we have one dipole in this molecule, one dipole in this molecule. Is that clear? So the first one is going to be dipole, dipole. Another example can be, for example, a carbon with hydrogen, 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 and chlorine. Yes? It doesn't matter which is the name right now. We are not talking about the names. But again, we have this molecule. Let me see if I can rotate this. No, I cannot rotate this. Okay, it doesn't matter. So we have this, oh my God. So I rearranged the molecule now, and you can see that again, I am going to have a molecule that is polar. Where is the more negative side? Where is the negative dipole? For the chlorine. So this is going to be the negative side, and this is going to be the positive side of the molecule. That doesn't mean that they are ions again. Okay. Now what we have here, and I'm going to do it in this one too, so you can see. In this one, we are going to have the electrons shifted towards which side? From the hydrogen to the chlorine, yes? We represent that like this. An arrow with kind of a cross in the beginning. That means the electrons are shifted in the direction of the arrow. Do you follow me? So that is going to be a dipole. In this one, we have another dipole. And I think we saw this when we saw the shape of the molecules. Yes? Now, between this one, where are the dipoles? Well, we have a dipole here. Yes? We have another dipole here. We have another dipole here. And besides that, the carbon is less electronegative than the chlorine. So we are going to have a dipole here too. In general, we are going to have the electrons going to the chlorine. Yes? That is going to be the resultant dipole moment. So this is going to be the density positive, and this is going to be the density negative. Again, they are not charges, they are densities, meaning the electrons are going to spend more time in the negative zone. Is that clear? Okay, so if I have, again, another molecule of the same thing, we are going to have a hydrogen, hydrogen, hydrogen. This is a hydrogen, okay, with a carbon and with a chlorine, and this is going to be the dipole-dipole bond. So far, so good? Now, these compounds normally have less melting and boiling point than another compounds that we are going to see next that are a special kind of dipole-dipole. They are dipole-dipole, but they are special. What is the specialty that they have? Well, in the special dipole-dipole, we have, let's leave a space for the name later. They have to have hydrogen. Hydrogen needs to be present. And you're going to say, hydrogen was present in the ones that we did before. Yes, but another thing has to be. First, it has hydrogen. The hydrogen must be attached to the following elements, and only the following elements. Look at the top right of the periodic table and tell me which are the three more electronegative elements you find. Fluorine, what else? Oxygen and nitrogen, and that's it. Those three are the only ones that are going to form this special dipole-dipole